Welcome to module 9 of the course time dependent quantum chemistry. In this module we will go over time dependent approach to energy resolved spectroscopy. In general, when you think about TDSE, time dependent Schrodinger equation, we get a feelings that it is going to give me a time dependent wave function, and if I have time dependent wave function, I do not have any access to the spectrum of the system. On the contrary, in this module we will find out that solution to the TDSE can give us the spectrum as well, and that is what we are going to go over. So, conventional approach to energy resolved spectroscopy. When I say energy resolved spectroscopy, I would like to know the spectrum of the system. If we follow the conventionally what we do and what we have already realized, that time independent Schrodinger equation, which is given by this equation, time independent Schrodinger equation for a quantum system provides stationary eigenstate energy En and eigenstate wave function psi n is provided, they are provided by the time independent Schrodinger equation. These eigenstate wave functions are orthonormal in nature, that also we have understood. Generally this is going to be orthonormal in nature, which means this is going to be delta mn, where delta mn equals 1 if m equals n, and it is 0 when m not equals n. So, each state which is a solution to the TDSE are actually orthonormal. The solution to the TDSE provides the spectrum, a structure featuring where the energy states are. So, this is a typical example. If the energy states are here, so I can get a structure here. If energy state is here, I can get a structure here. If energy state is here, I can get a structure here, and so on. So, solution to the TDSE provides the spectrum of the quantum system because it gives me the energy states, and that is exactly what is important in energy resolved spectroscopy or in frequency resolved spectroscopy. Of this frequency and energies, they are related by omega equals, if it is En energy, then omega is going to be this En by h cut term. So, the basic idea of the energy resolved spectroscopy is that we need to know the energy states, and that those energy states can be obtained from time independent Schrodinger equation. That is something which we have understood from very basic quantum chemistry class. This is just an example following the same conventional approach. We are very much familiar with this particle one dimensional box problem. We have been doing it for a long time, and in the particle in one dimensional box problem, the Hamiltonian is given by this, where more specifically we have written the parameter L. So, it depends on the parameter L controls the overall Hamiltonian, the potential which will be experienced. So, the basic idea is that if it is a free particle in a box problem, then V x L equals 0 when 0 is x is greater than equals 0 or less than equals L, and V x, this is semicolon. We should remember the semicolon we have used always in the adiabatic theory, we have used it to separate the variable and the parameter. So, it is going to be plus infinity when otherwise. So, this is the definition of the potential. The particle in one dimensional box is experiencing this potential, and that is why we get the wave function, the nth wave function and nth energy state. And if we know the energy states, we know what kind of transition in the spectroscopy we can have, different transition we can have. These transitions occurs within the eigenstates. So, that is why in energy resolved spectroscopy, knowing the energy states are very, very important. So, this is a very general consensus. We have been using this general consensus for a very frequently in quantum chemistry. On the contrary to our conventional approach based on time independent Schrodinger equation, what we are going to now present, and we are going to realize that it is possible to determine the eigenvalues and eigenstates for any one dimensional potential. We are continuing with the one dimensional problem. So, this is possible to explore directly from the solution to the time dependent Schrodinger equation. So, this is called time dependent Schrodinger equation. We are very much familiar with it, and we will see that this solution to this may give us eigenstate energy and eigenstate wave function for given Hamiltonian. So, yes, it can TDSE can explore the spectrum of a quantum system. This is what we are going to see. And in order to realize that, what we need to understand is called Wavepacket correlation function. What is Wavepacket correlation function? We have understood that for a given initial wave packet, let us say I have a particle, initially the wave packet is representing that particle. So, I know initial wave packet which is x 0, this is the initial wave packet. For this given initial wave packet, either I can do analytical solution or numerical. Most of the problems needs to be solved numerically, but we can have analytical solution, particularly Gaussian wave packet. We have seen that analytical solution is possible for Gaussian wave packet. Now, for the translational motion. So, for a given initial wave packet psi x 0, analytical or numerical solution to TDSE gives the wave packet psi x t at any later time t. That we have seen that. Now, our task for this present module is to correlate the initial and final wave packets. So, what we need to do is that we have to do the correlation, how they are correlating. That is exactly what we are going to find out, and that is given by this correlation function. This is called Wavepacket correlation function. Wavepacket correlation function, that is the integration over the entire space. So, I had, let us say, initial, this is minus infinity to plus infinity x space. We have initial Wavepacket was this was psi x 0, and final Wavepacket, let us say this one psi x t. All we need to find out, we have to correlate it, and this kind of correlation is nothing but the overlap between these two wave functions. So, basically it is trying to explore this overlapping regime, how they are correlated, whether they are fully overlap, partially overlap. So, this is what we are going to find out. This is what is the meaning of it. So, if we can correlate it, we will be able to get an information of the eigenstate energy, and how we can do that. That's the exercise we will go over. So, we have seen, so the correlation function, Wavepacket correlation function is nothing but finding out how much they are correlated, how much they are overlapping with each other over the space. So, extent of overlap is going to be calculated through this correlation function. So, in order to do that, what we will do, we will follow the approach we have always taken up in this course. We know that this psi x t wave function of the particle of a quantum system at time t, one can say this is the Wavepacket, can be expressed as a linear combination of orthonormal eigenstates. So, let us say I have an Hamiltonian, that Hamiltonian is giving me, should give me, if I solve TISE through TISE, it can give me all these energy states. So, let us say one energy state is psi n. So, this is going to be psi n minus 1 and so on. Okay, all these energy states are given, and energy their eigen values are E n, then this is going to be E n minus 1, like this way. So, associated eigenstate and eigenstate energies are there. This is a stationary eigenstate. So, basically what we are going to do is that expand the wave function in using, you are going to use that using the orthonormal stationary, they are all stationary because TISE gives me stationary states, orthonormal stationary eigenstates of the quantum system. So, that is the way we are going to expand. If we expand it, then we can have, we know that it is going to be Cn expansion coefficient, which means that at time, this is a non-stationary wave function. This non-stationary wave function are represented in using the linear combination of stationary wave functions. And what contribution, which stationary state contributes the most at time t, that is controlled by this Cn. So, Cn is giving you the population at the nth state. These are usual meaning. We have been using this meaning for a long time in this course. So, this is the, so we have the time independent part, time dependent phase factor, and associated expansion coefficient, which is going to control the population at time t in that state. So, this is the way we can expand the total wave function at time t, and as a result at time 0, t equals 0 time, I will be able to represent the that's the entire thing. So, in that case t equals 0, so this phase factor will be gone. What I am going to do is that to make it as a general, I will just change the index, the designation or the notation of the index. So just to make it a general, because it will be useful to use these things. And theoretically, we know that m will be extending, index would be extending from 0 to infinity, n would be 0 to infinity. Basically, all states, possible states, stationary states will be added together, and Cm is showing the population at that state. So, I have just what I have done is that I have selected two different indices for my convenience, one to represent this one, another to represent this one, but the meaning of these indices is the same. There is no change in the meaning of the indices. So, I have these two functions. So, all we need to do is that to find out this time correlation function, I need to add these two into this function. So, I have to include it. So, that is exactly what we are going to do now. I have these two functions now, and I am going to now insert them here. If I insert it, then what I get here is that minus infinity to plus infinity summation of m c m star. This part is the complex conjugate, that is why c m star 0, and I have now psi m star x, then summation of n, then c n t psi n x e to the power minus I e n t by h cut. Then the integration is over the entire space. So, this is what we get after inserting these two expressions into the time correlation function. And after that we can reduce it very easily. We can reduce it very easily in the following way. I can have these two summations together, then Cm star 0, Cm star, they can be taken out, Cnt they can be taken out because they are pure time dependent part, and this integration is over the space, that is why we can take it out. Then Cnt, and this time dependent phase factor can also be taken out because it does not depend on the space. So, in the end what I get is that the summation looks like this, minus infinity to plus infinity. This is going to be psi m star x and psi n x dx. And we can recognize what is psi m, psi n. They are the stationary states of the Hamiltonian H. So, if the system is representing an Hamiltonian, and still we are considering it is a time independent Hamiltonian. So, I have an Hamiltonian which is time independent, and that is giving me not explicit time dependent. So, that is the way we should put together. So, for this Hamiltonian I have this eigenstates, all these eigenstates, and the population is changing as a function of time, and that is exactly what we are trying to find out. So, I have this psi m and psi n, they are actually representing these stationary states. That is why this part can be approximately can be represented as a delta function. So, if I represent this as a delta function, so what I get is that I have these summations over here, and then 0 Cnt e to the minus I nt by h cut, then delta mn. And we know that delta mn takes only two values. For for m equals, for all m equals n, I will have the value. If m not equals n, then it's going to be entire thing will be 0. So only terms which will exist in the end in this summation is going to be when m equals n, and which means that I have this summation remaining C n star 0, then C n t, then e to the power minus I e n t by h cut. This is what we have remaining. So finally, the another form of the time correlation function which we get is this one. This is the form of the time correlation function. So this summation, this particular summation will be all 0, all terms of this summation would be 0 except for that term for which m equals n, and that is why this summation will exist. We are writing here, but this summation, when we are writing explicitly each term, all terms will be 0 except for m equals n term which will exist. Okay. So we have been able to get another form of the time correlation function, which is correlating the wave function at t equals 0 and wave function at a later time t. This time correlation function, now what we will do is that we will Fourier transform the Wavepacket correlation function. So we have this Wavepacket correlation function Ct, and we will Fourier transform it. This is the way we do Fourier transform. It is just a convention. So if we have a function, let us say if we have a function and I am converting into frequency domain, time to frequency domain. So it is going to be time to frequency. If we do the Fourier transform, we will see what we have, basically what information is hiding within this function Ct, that will be able to explore in the frequency domain. If omega, if we are doing it like this way, if omega equals plus minus ft, if we consider ft to the power minus I omega t, then inverse Fourier transform would be e to the power plus I omega t. On the other hand, if we take this representation where time to frequency domain representation is plus, then frequency to time domain representation, when we will do inverse Fourier transform of this, then we will have to use minus I omega t. So whether to use plus I omega t or minus I omega t, it depends entirely on the convention or the representation of the Fourier transform we are going to use, and corresponding inverse Fourier transform has to be selected accordingly. So here we are considering plus omega I omega t. There is a reason why we are doing it, because it will give me a very interesting outcome, very interesting information which will emerge, which is hiding within this time correlation function. So let us do that. So if we do this integration, we have to just now insert the form plus infinity. Ct is now going to be n Cn star 0 Cnt e to the power minus I omega nt. This is going to be over the time, and as we can see that one can say that this Ct, this is more like an envelope function. So I have, let us say, Cnt e to the power I Cnt e to the power I. So we have here another term e to the power I omega t as well. Yeah. So what we see here is that, recollect this information from a pulse. We had a envelope function which was represented by at, and then I will clearly write it. If we recollect the pulse formation, we had or Wavepacket formation, we had an envelope function at, in the time domain, in the we consider the pulse, and then e to the power I minus I omega naught t. That's the way we have represented, which was slowly varying and fast varying components we have got. And we said that this part is very slowly varying component. So if this following the similar note, if we consider that the CT, although it is time dependent, but it is varying very slowly as compared to these terms, these two oscillatory terms, then we can take it out from the integration and we can actually write down 0 CNT, then integration is going minus infinity to plus infinity, e to the power I omega t, e to the power minus I omega nt dt. This we can take out, this CNT we can take out under the assumption that CNT is slowly varying, with respect to e to the power I omega t or e to the power minus I omega nt, both of them. It's slowly varying, that's why we have taken it out. And if we can take it out, then what will happen, we can recall the definition of the delta function we have already given when we are dealing with translational motion or Wavepacket dynamics. Delta function has one representation, which is omega minus omega dash equals 1 by 2 pi minus infinity to plus infinity e to the power I omega t e to the power minus I omega dash t dt. That was the representation. And if we, in the present context, if we try to do similar representation, what we have here, we have e to the power I omega t, and instead of omega dash we have omega n. So we can write down as omega n. So this is going to be then omega, this is going to be omega n, and that's the representation we have. So this equation, this integration is actually representing our delta function. How we are going to write it down? And if it is delta function, then the integration is going to be done 2 pi, this part will come here. So this integration is nothing but 2 pi delta function, and that's exactly what we are going to insert here. So we can write it down in terms of delta function. This is nothing but summation of Cn star 0, then Cnt, and then the delta omega minus omega n, and there is a 2 pi term also. There is a 2 pi term. So we have 2 pi this function. So what we see that the sigma omega, which is representing the Fourier transform of the correlation function, it is given by this, and there is a meaning which you can immediately find out from this, where omega n equals nothing but En by h cut. En is the eigenstate energy. So what we get is that this Fourier transform of the correlation function gives me a spectrum, because this is actually representing a spectrum. This is representing a spectrum. Why this is representing a spectrum? This will exist, this delta function will exist only when omega is omega n. What is omega n? Omega n is those states, representing those eigenstates. So whenever omega, and omega is continuously varying, so I'm going to vary omega continuously, and I will have function value only when the states are matching with this omega. So I will get a spectrum, and that's all about the spectrum, spectroscopy, energy resolved spectroscopy. I get the energy states, which is modulated by this function. So I will be able to plot now this sigma omega as a function of omega, and I get the max function value. This is kind of an, this envelope is represented by Cn star 0, Cnt. that is the way it is representing. So, what I need to do is that I need to find out at time t what is my wave packet and correlate it with respect to x0. Once we correlate it, I can Fourier transform that correlation function and I get back the spectrum. This is the way I get the spectrum. This function exists only when I have this is matching omega n, and omega n representing the wave function stationary states, each stationary state of the Hamiltonian. So, this is the way we are getting it. So, this exercise demonstrates that the Fourier transform of the wave packet, Fourier transform of the wave packet correlation function renders the spectrum of the quantum system and this is called time dependent approach to the energy resolved spectroscopy. It is quite interesting that through TDSE we are actually extracting the information of the eigenstates. We are not solving TIAC, time independent Schrodinger equation, to get this. We are actually solving TDSE, time dependent Schrodinger equation. We are starting with an initial wave function and we are allowing the system to evolve following time dependent Schrodinger equation, and we are then after a certain time we have to select this wave function at time t, then correlate them, which means that we have to find out the extent of overlap, and that overlap is going to now, if I Fourier transform, that overlap has that information, how many states are there and what states we have, but we cannot see it in time domain. We have to, in order to see that, we have to go to the Fourier domain or frequency domain, and immediately we will be able to see that. So, this entire exercise gives us an interesting perspective of the time dependent Schrodinger equation. We have been finding out the correspondence between time and frequency. We will stop here and we will continue this discussion in the next lecture.